Good evening, everyone. Um, First of all, I thank the Oncology Club Scientific Committee and like the entire Oncology Club organization for providing me the opportunity to be here. My topic of today's presentation is about advancing in CT quality assurance in radiation oncology using Pilonac automation. Now, automation is something really it's going to be artificial intelligence is obviously it will take another 4 5 years. Some of the part of an artificial intelligence has been already we are using clinically in a little bit of a lower scale, but obviously it is going to increase in the future. But automation is something it's really going to helpful, and it's all already we are in the lot of process of radiotherapy process. We are already applying automation. It's really going to improve our precision and consistency. It is really going to enhance our treatment personalization, and obviously it is going to improve your efficiency and accessibility and safety of the patients and quality assurance. We can obviously you can use an automations there to improve your outcomes. So in this, there are a lot of commercially available softwares available, but just I want to give a single example. Just I want to don't want to talk about automation for an hour, but I want to give a single simple example about how you can use an automation in your clinical thing, so that I just there are open sources available like Pylenac, PyDicom, which are really useful. You can do a lot of automation in your clinical process. If you're able to map your clinical workflow, obviously we can do a lot of manual work. We can easily automate into your clinical process. Pylenac is Python library, which has a lot of tools which to cover the TG142 QAs. And normally what it does is we can input the images and we can get an output in a numerical format and in the plots. And it obviously it consumes a lot of raw data and images, and it gives an useful informations where normally and manually you cannot achieve it. And it gives a meaningful data like which we cannot really see by our human eyes. Okay, so normally in the Pylinux module, just I took only one module for the demonstration purpose. Just I'm going to demonstrate about the CT QA process, how you can use in Pylinux, because already the library is there. You don't require to use much of the codes. Just it's a simple 4 line code. You can execute the entire CTQA into just for 3 or 4 lines. It has a library of four CT CAT data like 504, 503, and 600, so that most of these phantoms are available along with your missions. So you can use this data for your CTQA and as well as for your CBCTQAs. Okay, Pylenac, the one thing is it is not a database, so it just it runs and it gives the result. But what my plan is that we are planning. I already done half of the work. Like we are going to plan a proper software, and we create a database so that you can see the trends of the entire QA for your years and years to years data, and we are going to freely give it to the subcontinent people to use it for the clinical purpose with proper testing. After proper testing, we are planning to give it on a free without any license to our subcontinent people. And obviously we need to be very careful when you use your open sources. You need to have a proper testing and everything has to be done, and obviously it is an open source without any commercial licenses. I will just show a small example about what are the modules available. I have not taken the entire module. You can see a star shot pattern. Like normally what you do is during the commissioning, you do just irradiate a flame with an star shot, but it's very difficult to analyze what is the results there. Okay. So normally now what we do is we use it using an epid based star shoot. You send these images to the Pylenac, just 3 lines of the code. You can see the pixel values here, and normally you can read what is then your collimator isocenter there, whether it is 0.3 millimeters or a 0.2 millimeters, which is not possible with our really a human eye. What is the exact your collimator isocenter tolerance, whether it is within the tolerance? Just what we see in your eyes is just like that. And other things are it saves a lot of time. Tomo cheese phantom, put a lot of region of interest automatically. It gives us a HU value, and we can easily see whether it is under the tolerance. And picket fence, like we do a lot of QAs, and it is really very difficult to analyze. So it gives data in submillimeters. So it's really, really useful. And planar imaging QA, normally you go and see the line pass, and really it gives values like, what a human eye cannot see there. And Winston laws, it's obviously difficult. Like, so also it gives us a good information in a 3D way, like where, like, we cannot see in our normal approach. So all these modules are available, and we don't require all the codes to be done because the Pylinac has all the codes. Just you have to write few lines to execute your data, and you have to tell your data where your data are. Okay, so obviously, for the CTQAs, these are the TG reports available, like obviously report number 233, and TG66, which are the common, which one we use it. And for the Pylinac CTQA module, what it does is, it has a reference data inside, so that when you push your data, the CT data inside, not normally what it does is try to register with your reference data. And so that it understands the DICOM coordinates there. It put the region of interest, and it takes the measure the values there. And you can do any scanning protocols, so that's a good leverage you have. And it's totally an automatic testing tool. Okay, I will, like, this is what the software I use in my clinic. We use an Aqua, which we pay like $200,000 to do this. And what we do is we push the data inside the Aqua, and we select the phantom, and we run the analysis, and it gives a lot of information. And like, it gives your laser alignment, it gives your slice thickness, whether it is inside the tolerance, like it gives your low contrast resolution, HU linearity, everything. The same thing, like what we are paying for $100,000 for the commercial tool, like, which is available in the open source. If you are able to put a little bit of an effort in a coding, you are able to achieve by yourself. And as low income countries, like, really this kind of a thing is really going to helpful. And like, probably as a medical physics, we don't focus only on the treatment planning and the quality assurance. We try to develop our own tools to do, or like, automated way of doing it, as well as it will help us to try to understand the workflows, and it will create efficiency, as well as it will create you, I give you a lot of understanding about how things are happening inside that. So that's what it's more important. So so this is what it does, like, we use a commercial software for this. Okay, let us get into the Pylinac. If you use this, like, what you can do it is, you can view sorry for the bad image quality here for the display. The HU uniformity, the HU linearity, and the modulation transfer function, the spatial resolution, broad contrast resolution, and the uniformity profiles, it done like within 3 seconds. I will show you a demo of like how long it takes to run this program. So that's what I know. I use my laptop just to run this program here. Okay, so that the HU linearity here, like, the single slice, once it maps the registration, it goes into the particular location. It measures the value between the scales, whether the linearity is okay, and whether it's within the tolerance limit. It can tell us whether the QA is passed or not. Your slice thickness are okay. It has an algorithm to find that, and whether your geometrically line arrangements are okay or not. And everything can be done within that. And HU uniformity also calculator, and you can change your region of interest, so that whether you want to have a smaller one or a larger one. And this is a spatial resolution and the modulation transfer function, which it calculates automatically. And so that how the code looks is just, it's a 3 or 4 lines. Probably the display is not that great. Okay, just I will explain. The first line is just you bringing your Pylinac library into that. The second one is you are locating. The second line is just you're telling where your DICOM data are. And the third line is just you're going to analyze the images. That's it. Okay, so that you can print the data in a PDF, or you can assign the tolerance. You can change the tolerance according to your baseline of your data. So these are the 4 lines you have to write it down. Sorry for the bad quality. So what you can do is you can set up the tolerances for the HU linearity. Okay, I want the water to be within plus or minus 5 HU. You can set up a tolerance for everything for the low. So whatever the baseline of the machines, you can set up the tolerance here. Okay, just I will quickly give a small demo of an Pylinac, how long it takes to run this code. Okay, this is already the code, like probably it will take a couple of 20 to 30 seconds. So it gives the results, like if you want to result to be printed on the command prompt, or if you want to print it as a PDF also, you can do it. Probably, yeah, like maybe 10 20 seconds, sorry about that. So what I mean is, you can, like the same process, if you want to calculate all these parameters manually, it is going to be a 2 to 3 hours work of a physics, which you can generate within like something about 2 to 3 minutes. Okay, so it is going to really save a lot of time. And if a lot of people use a commercial software, there are a lot of open sources in GitHub and Pylinac, PyDicom, which is a lot of already a source of programs and source of codes, free codes available there, and really it can be used in a clinical situation. You can see that all the results has been here, and it gives us a result here, and you can print this one. What I'm working on this is going to create a database on that, so that you can save this and you can see the trends over there for the years. And it also, I will close this one, and it also creates the PDF format of that, you can print it and save it. So in summary, it's an really a good automation tool, it's a good open source, and it does in registration, and it takes the data. It supports multiple cat data phantoms which are available in our clinical use. And we can take an output as an all the QA parameters can be taken out. And Pylinac enhances QA efficiencies, reduce manual errors, ensures robustness, repeatable analysis of CT or CBD system, everything it can be done. And these are the automation resources available. You can go to GitHub, PyDicom, Pylinac. There are a lot of resources available. You can utilize that. And thanks for your time. And thanks for the Oncology Club for providing me the opportunity. Thanks a lot. Okay.